Alright, this is going to be section 3.3, logarithmic functions and their graphs. So remember in the last section we called an exponential function, it was f of x equals a times b to the x, or anything that's just b in the form b to the x, we call that an exponential function, right? Exponential function. Logarithmic functions are the inverses of exponential functions. So a logarithmic function with a base b looks like this. We say log base b of x. This is a logarithmic function. It is the inverse of an exponential function. And now we can pretty easily change between logs and exponential form. And how we do that is that when we have a log function, it's y equals log base b of x, and that's really the same as, so I'm going to put an arrow going both ways, it's really the same as the base to the y equals x. And we're going to do a couple of examples so you can kind of see how this happens. Our first example, I'm going to call this one letter A. I want you to solve log base 2 of 8. And we're going to set that equal to y for now. So what we have to think about when we solve this is our base 2 raised to the y is equal to our x, which in this case is 8. So you have to think to yourself, 2 raised to what power is equal to 8? Well, we know that 2 raised to the third power is equal to 8, so that must mean that y is equal to 8. So now we can finally write our expression log base 2 of 8 is equal to, let me go back. So y is equal to 3. So log base 2 of 8 is 3. Let's try another example. I'm going to call this one letter B. What if I give you log base 3 of root 3? Well, we know that's really equal to y. So we have to think to ourselves, 3 to what power is equal to root 3? And we know that 3 to the 1/2 is equal to the square root of 3. So that must mean that y is equal to 1/2. So now we can write our function or our expression as log base 3 of root 3 is equal to 1/2. That would be your final answer. Let's try a couple more. Letter C. Log base 5 of 1 over 25 equals what? Log base 4 of 1 equals what? And the last example we're going to do in this case is log base 7 of 7 equals what? These last two here are pretty common and they're pretty easy, and I'm going to show you why in just a second. So if you go back to this first one, you can see that this expression is going to be equal to -2. And that's because 5 to the negative second power we know is really equal to 1 over 5 squared, which is really the same as 1 over 25. That's how we check our answer. In letter D, log base 4 of 1 is equal to 0. Well, that's because 4 to the 0 power is 1. Remember, anything raised to the 0 power is 1. So if your base is ever just 1, your answer is always going to be 0. Or whatever your expression is equal to is always going to be 0. It doesn't matter what the base is. Anything raised to the 0 power is equal to 1. Same thing happens here when our base and our x value are the same. We know that log base 7 to the 7 is equal to 1 because that means that 7 raised to the first power is equal to itself. So anytime you have a base and your x value the same, your answer is always going to be 1. We have some common logarithms, and the most common logarithm is base 10. So I'm just going to write common log so we remember. Common logs base 10. We like when we have base 10. It makes it a lot easier. And all this really means is we have log base 10 x, and you'll see that written sometimes as just log x. If something ever just says log a number and doesn't have a base, we assume that it's 10. So this means that y equals log x is the same as, so I'm going to put arrows on both sides, 10 to the y is equal to x. Those can go back and forth. Remember, they're inverses of each other. So let's try a couple of examples with log base 10. Our first example is going to be log 100. And remember that when we have log with no base, we really know that there is a 10 there, so you can imagine a 10 there, or you can write it in if that's helpful to you. We know that that answer has to be 2. And that's because 10 to the second power is equal to 100. So now I'm going to give you 3 more examples that I want you to try. Example B is going to be log, and then base 10, I'm not going to write it because we don't need to write it. The 5th root of 10, log base 10, again, I'm not going to write it because we know it's there, of 1/1000th. And then finally, this one's going to be a little bit trickier. 10 raised to the log base 10 of 6 is equal to what? So let's go back to letter B. In letter B, the answer is going to be 1/5. And we can check our answer again by saying that 10 raised to the 1/5. We know when we have something raised to a fraction, it's really just taking that root of the denominator, so the 5th root of 10. In letter C, our answer is going to be -3. You can see log base 10 to the -3 is the same as 1/10 to the 3rd, which is the same as 1/1000. And then this last one is a little bit trickier. This last one, the answer is going to be 6. And we're going to have a lot of examples that look like this, and this is a log rule that we're going to be talking about quite a bit. When you have some number here and it matches the base, so our base in this case is 10. If I have 10 raised to a log with the same base, your answer is always going to be whatever this number is. So for example, if I had 2 log 2 7, because I'm raising 2 and it has a base 2, my answer would be 7. Make sense? Alright, now we're going to use these applications to solve simple log equations. And we're only going to have 2 examples here. Our first one is going to be log x equals 3. And most students find this the easier way to go about it because you don't really have to think about it. It's an equation that you solve versus trying to think of what fits into the equation to solve it. So how would we solve for x here? We know that our base is 10, so we know it's going to be 10 raised to the 3rd power is equal to x. Well, 10 raised to the 3rd power is 1,000, so x is equal to 1,000, and that's your answer. Our example B is going to be log base 2 of x is equal to 5. So again, you're solving equations here. Solving equations. This time we have a base of 2, so we're going to have a base 2. It's raised to the 5th power, and that's equal to x. Well, we know that 2 to the 5th is really 32. So x equals 32 would be your answer. Just like we had common logarithms, the base 10 logarithms, we have natural logs too, and we talked about this in the last section and the section before, the letter E. So these are going to be natural logs. And natural logs have a base E. Surprise, surprise. In this case, we could say log E of x is really the same as ln of x. This is the notation that we use for the natural log. I don't know why they call it ln instead of nl, but I think of it as natural log. They're backwards. So these two things mean the same thing. In 9 out of 10 cases, you're going to see it written as ln x. Remember that ln of x is the inverse of its exponential function, and remember its exponential function is f of x equals e to the x. If those things are true, then that means that this has to be true. If I have y equals ln x, then this goes both ways, that e to the y is equal to x. And let's try a couple of examples with natural logs. Starting with example A, you're going to do the natural log of root e. Well, we know that the natural log really means that there is an e right here. We just don't write it. Sort of like the base 10. When we have a natural log, there's really an e there. We just don't write it. So right now, we're trying to figure out e to what power is equal to the square root of e. Well, we know that e to the 1/2 equals root e. So that means that y must be equal to 1/2. So now you can write your final equation as ln root e is equal to 1/2. Let's try another example. This time we're going to have ln e to the 5th. Remember, again, same thing. I didn't write it there, but there really is an e there. And because we have a base and an exponent, and the base of an exponent the same, our answer for this one is just going to be 5. This is one of the special cases that you'll see. Letter C is also a special case, similar to the base 10 again. If I have e raised to the ln 4, just like I said in the last couple of slides, we know there's an e there, so if I have a base up here and it's raised, the base is raised to the same base, your answer is just going to be 4. And finally, we're almost done. It's a pretty short section. All we have to talk about now is the graphs of these functions. I know it's everyone's favorite part. These are going to be graphs of log functions. So we're going to talk about the natural log function. F of x equals ln of x. It's generally the graph we talk about the most. So we're going to do that one first. If this is my coordinate plane, the graph of the natural log function will always have this general shape. Maybe I should have done that in a different color. Let's see if I can get it to turn red. The graph of the natural log function. So again, f of x is equal to ln of x. The graph takes this shape. Now, if we don't transform this graph at all and it stays exactly the same, we know that our domain is going to be from 0 to infinity, because you'll never be able to substitute a negative number in for x. It will never work. Our range is always going to be, or for this graph, going to be all real numbers. Our vertical asymptote is x equals 0, approaches 0, but never actually gets there. We don't have a horizontal asymptote. And for our end behavior, the limit as x approaches infinity of ln of x is equal to infinity. So it's constantly increasing. As x gets bigger, our graph ln of x is always going to get bigger, so it approaches infinity. The last type of problem that you're going to see in this section is transforming the graphs. So just like we did in the last section, we're transforming the graphs. Starting with letter A, you're going to try these. ln of x plus 2. Letter B is going to be ln of 3 minus x. Letter C will be 3 times log x. And letter D is 1 plus log x. Now remember, these have the same basic shape as the natural log function. We generally just talk about the natural log function. So you want to tell me what happens to these graphs. From the original graph, what happens to these graphs? In letter A, you're changing the x value, so that means it's going to be a horizontal change. And horizontal is always backwards, so because we're changing the x value, we're going to shift to the left 2 units. In letter B, again, you're changing something to the x. This is really a positive 3 in front, right? We just don't write the plus sign. So that means that we're going to be shifting this graph 3 units to the left, and then we're reflecting over the y-axis because we have a negative sign in front of the x there. So shifting 3 units left and then reflecting over the y-axis. In letter C, we're multiplying 3 by the entire function. We're not actually changing our normal function. We're multiplying the entire function by something. So that means it's going to be a vertical change. It's going to be a vertical stretch by a factor of 3. And then finally, in our last example, letter D, we didn't do anything to the normal function. All we're doing is adding 1 to it. So that means it's going to be a vertical shift up 1 unit. A vertical shift up 1 unit. And those are all the notes we have for section 3.3. We'll be doing example problems in class.